This is Cosmographia, the Randall Carlson Podcast. Okay, ladies and gentlemen, welcome back to the Kosmographia podcast. We are here in the depths of the Northern Hemisphere winter solstice. And so it's the 3-day pause of the sun. I am enjoying it because the nighttime is the right time. So go outside and worship the dark gods. How's it going, Brad?
In your black shirt. Man, right. I'm doing excellent. I enjoy the season. I'm getting to play a little bit of Santa Claus myself here.
All right.
Yep. So doing good. How about you guys?
We're doing great.
Yeah, doing good.
Randall, sir. How are you?
Oh, I'm doing well. I am doing well. A few bumps, in the last couple of months.
Yeah.
Getting my expedition totaled. Guy running a stop sign slamming into me.
Literally bumped.
Yeah. So I've been dealing with that. I was over at the Department of Motor Vehicles today, trying to get an updated title on the thing because I actually don't know what happened to the title. I paid the thing off 10 years ago, and there's some box of things from 10 years ago when I know it's in there, but hey, I didn't ever think I was ever going to sell the thing, so I just didn't keep up with the title. So they said, well, if I want to get my settlement, then I got to turn over the title to the insurance company. Okay.
Yeah, he's still got the 1983 van sitting there next to the garage.
So well, I'm thinking I might just get that thing running again.
He was going to mothball the expedition too.
No, it's gone. It ain't there no more.
That's a bummer. That's a loss of the family there, man.
I know. It was like losing a family member.
Yeah.
It was. Well, I used to talk to my truck, if I was feeling a little depressed or whatever, I'd go sit in my truck and we'd have a conversation and,
yeah, sure.
We were old friends. I took
care
of him.
Laughing, I'm trying to, this is a solemn occasion.
It is a solemn occasion. And, no, I've processed it and, I'm ready to move on now.
Okay.
So, and then, my brother-in-law bit the dust about 3-4 weeks ago.
Yeah.
Yeah, that was a little bit rough on the family.
That is rough.
Yeah, but
hey. Another accident of alcohol. It's hits many families. It's hit mine in the past.
It hit ours as well.
Yep.
Anyways, but it's not what we're here to talk about.
Nope.
Let's talk about a little bit about our last podcast with our first official guest.
Yeah.
George Howard.
That was a great
show. Yeah.
Yeah, he lit it up. That was awesome.
So it's interesting the way that whole thing has evolved over the last, now we're going on 12 years since the Firestone paper was first published. And there's been a lot of ins and outs and what have yous.
Can you give a little like a short breakdown of how you guys met, George, and like how did that happen? How did you guys,
Well, let's see. Good question. I know. I mean, we participated in that roundtable out in where were we, Brad? Charlotte?
No, that was Wilmington. We did with Graham and Antonio Zamora and Michael Davies and some of the common research guys. Yeah. But no, that was post initially meeting him. I think you had corresponded with him just about Carolina Bays in the past.
Yeah.
Not knowing that he was involved with Common Research Group at that point.
Maybe so.
And then it's like, you're doing that also? Yeah, well, we need to talk to you.
Well, yeah, because then I remembered that his name was on that seminal 2007 paper.
That's right.
Yeah. And then we met the guy and found out that he was a likable fellow. We had a lot of good times and good laughs hanging out with him. And it's always good to meet somebody that's a congenial personality and also knows enough that you can actually learn something from them.
Yeah.
So, yeah, and I'm sure we'll be out in the field with George again, no doubt about it.
No doubt.
Yeah, maybe he will participate in the Scablands tour.
No, that would be great if George.
Well, he sure wants to, but yeah, anybody that's got the means to do some excavations of the Carolina Bays to see what's down underneath, yeah, we want to be involved with those cats.
Yes. Right.
Yeah, and for the sake of the listeners, I'm sure some of them are familiar with the Carolina Bay controversies. Others may not. We will at some point devote a show to doing the Carolina Bays. In fact, my interest in the Carolina Bays goes back to the 1980s. I have aerial photographs that I've taken of bays that probably were taken around 90, 91, right in there. So up to that point, I think my first awareness of the bays came probably early 80s. And interestingly, I think that the connection actually came with my very first interest in Atlantis, because I believe it was the Otto Mook book, Secrets of Atlantis. He was the German physicist, came out with his book, I believe it was 1980, and he devoted a section in there to the Carolina Bays. And his idea was that there was an asteroid impact into the Atlantic Ocean. And the Carolina Bays, as the asteroid, which was composed of friable material, as it's entering the atmosphere, it's already disintegrating. And the byproducts of that disintegration then descended down over the southeast coastal plain, really would have been more like in the form of multiple Tunguska type events.
Airbursts.
And I actually don't remember, I think he was actually describing a scenario of actual impact.
Okay.
But in any case, shortly thereafter, I read that, maybe a few years. I think that book came out in 1980, as I recall, and I read it shortly after it came out because I thought, okay, I was curious about Atlantis, and I thought, okay, well, now here's a physicist. Maybe this will be a little bit more of a rigorous treatment with a little bit more of a scientific basis to it than some of the woo that's out there. But that's what led me into the Carolina Bays. And then I realized, well, hey, these things are right in my backyard. So I think what it was, I went to, this would have been about 1990, I think. I was using here in DeKalb County, there is a library, a science library. It's actually a science center, the Fernbank Science Center. And they have a planetarium. They have an observatory there. They've got laboratories. It's a pretty cool place, and it's a lot of displays and things like that will rotate. They'll have a display maybe for 3 months and it'll rotate. But they have a science library there that was actually created for the public, for the use of the public. And so they had subscriptions to lots of science journals. They had a whole library of books on all kinds of scientific subjects. And I was primarily interested in the geology, the astronomy, the archaeology, that kind of stuff. So I spent a lot of time in that library. And I made friends with the librarian, and she was really interested in this research that I was doing. And so for about 2 or 3 years, I spent a lot of spare time over there in the Fernbank Science Library, and she would go through these, there was no internet then, so nothing was online, so she would have to go, but she had connections with all of these universities all over America, all over Europe. So I would need a paper. There would be a reference to a paper that I'd want, and she would go find it. And, a week, generally 2 weeks, 3 weeks, or a month later, an envelope would show up there at Fernbank and my paper would be in there. And so I have archives of literally hundreds of papers that I procured that way. So this was my initial studies. But then I got a hold of Henry Savage's book, the Mysterious Carolina Bays, that came out, and George referenced that book as well. And he had a bibliography in there of pretty much everything that had been written or published on the Carolina Bays up to that point, which, what was that, 1986?
I think that was 82, maybe.
82, yeah, maybe it was earlier. Yeah, 82. I didn't get to his book until about 90, so it had already been out a while. So what I did was read the book, found it was a quick read. I read the whole book in one sitting because it's only about 120 pages. And then when you add in illustrations and charts and things. At the end, though, what he had was this bibliography of pretty much everything that had ever been written on the Carolina Bays up to that point. So I spent the next several months procuring most of that bibliography. So working my way through all of that, and then that inspired me to actually get out. I went out. Me and Brad have an old friend, Jeremy. Jeremy and I took a couple of trips down to actually visit the Carolina Bays in the field. I went to a local airport, right in the middle of the
Tifton down there, I think.
Yeah, I think it was at Tifton, right? So there's a cluster of Georgia bays. So went down there, hired a pilot airplane. We went up in a little, I guess, single wing aircraft. I don't even remember what we were in, but did a flyover. So I took photos and of the Carolina Bays. Then while I was at there in the library doing the research, one of the scientists he was a PhD astronomer, and he was employed there at Fernbank Science Center, and he was working on his second PhD, which was in geochemistry. So somehow he heard that I was doing this research, and he came up and was really interested in the Carolina Bays. So he and I started kind of working together on it and made multiple expeditions down to collect samples at the Carolina Bays in Georgia. He has subsequently become, has now his second PhD a long time ago, I guess now in geochemistry. But he was the one that actually wrote the paper on the wood, where we went, Brad, the Woodbury structure in Georgia, which is a very
Warm Springs.
Yeah, down by Warm Springs, Georgia, which is where Franklin Roosevelt would go to get relief from the symptoms of polio. And there's a whole slew of these springs in this. It's like a crater. The Flint River runs through it. And it looks like a lot of fractured bedrock, a lot of access of thermal springs from below. So there's at least 7 thermal springs that have been documented in this area. And of course, this was sacred to the native people that lived there, who would make pilgrimages there to imbibe the springs and all that. So anyways, my point is this Ed Albin, he was the one who wrote the paper. So when Brad and I were actually going down there to explore this Georgia's probable impact crater for the first time, I was doing research to find out what background. That's when I discovered, this was my old friend Ed who wrote this paper on it. So we were using his paper as a guide when we went down there. And I'd been out of touch with him for a number of years, but he'd be a very interesting man to get on here and have some discussion with. One of the things that I did on several occasions with him was go down just south of Macon, where the fall line is, where the old Miocene, Pliocene ocean level would come up to. There's like a 200 or 300 foot bluff that runs all the way almost sub-parallel to the coastline. And what it does is it makes the transition from the Piedmont to the coastal plain. And at the fall line, there's an outcrop of the Eocene-Oligocene boundary, right? Now, the Eocene-Oligocene boundary is roughly about 35 million years old. And what's particularly interesting about that is that there was a mass extinction event at that boundary, and apparently 2 major impacts that are now well documented. One was an impact in Siberia called the Popogai Crater, and the other one is a crater that's about 50 miles wide. It's on the bottom of Chesapeake Bay. Right. So when that crater, in fact, I think when we were talking about last episode when we were talking with George, I mentioned Wiley C. Pogue, who was like the lead scientist who did most of the work on that Chesapeake Bay crater. So anyways, when that impact occurred, there was, of course, major amount of debris and material ejected up into the atmosphere, right? A lot of this was molten. So when this molten material falls back to Earth, it solidifies while in its atmospheric transit. And depending, I guess, on air currents and moisture and composition, a number of factors will determine the shapes of these things as they're coming down and crystallizing. And they can be spherical, they can be elongated cigar shaped, they can be dumbbell shaped, like they're almost like two of them with a connecting section. They can be almost pyramidal looking. Yeah, they can, and I should mention these are called tektites, right? Mm-hmm. So my point is at this particular outcrop along the fall line is where you can find a lot of tektites, because when this impact occurred, this material shot up into the atmosphere and it rained out over the southeast. So you had the landscape that existed 35 million years ago at the end of the Eocene. That landscape got bombarded with this molten material falling, but by the time it hits the ground, see, it's solidified already. But so now you have this rainstorm of this stuff coming down, hits the ground. Now the whole ground is covered with that. But now over 35 million years, that Eocene landscape gets buried. And so this is what happened. So only where you can actually access that place. So along the fall line, what you do is you go down there, and typically you want to wait until after a heavy rainstorm, because now you've got that bluff, and that Eocene-Oligocene boundary is in there, buried under 100 feet of sediment. But right there at that boundary, there's an exposure of it. So say during a heavy rainstorm, it's going to erode the hillsides, and it'll wash out tektites. And if you're lucky, you can walk along and find these tektites laying there. And there's a whole exhibit of them over at Fernbank Science Center that Ed collected, going down there and knowing where to look for that Eocene-Oligocene boundary. So it was very, very fun, very interesting in doing that. And we did make collections of stuff from the bays themselves, and there was some very interesting materials in the bay rims. And one of the materials now, and maybe we can get Ed on here to talk about this, but he had some of that. He was in his geochemistry program at the time, and he had this kind of slaggy glass, and I think it was they used argon isotope dating on it. And the idea is that, I forget right off the top of my head what the half-life of the argon is. Kyle, you could easily look that up if you're just sitting there twiddling your thumbs. But the idea was, the first thought was, well, if it's this glassy-like material, this vitreous type material, it's probably some byproduct of industrial processes, right? And that would be the first dismissive assumption that one would make, right? But in the argon process, argon gas is created, and it can actually be entrained in the little bubbles within the material. And by looking at the ratios of the two argon isotopes, you can get a sense of the age. And because of the slowness of the isotopic transition of argon, it doesn't really show up until you've got 10,000 years old or so. But what I remember, and again, I don't want to butcher this too much, and if we got Ed on here, he would probably specifically spell it out, describe how it all worked. But the point was, there were traces of argon gas that, as I recall, he said would mean that it was a minimum of 10,000 years old. So there was this slaggy vitreous glass associated with the Carolina bays. And of course, a few samples from one bay is not going to prove anything. But what it would take is probably a more exhaustive or rigorous, sampling of, maybe a dozen bays, and see. And also there are a lot of little spherules that show up microscopically, and I have not seen an analysis of those. But yeah, when we're listening to, Tony Zamora, he's got an idea. He's got his idea of the Bay Formation. Chris Moore has his idea. Davias, is that how you say his name, Brad? Davies? They have different. Yeah, close enough. Yeah, there's many different ideas about the bays. They're still very controversial and not explained. So,
what's the prevailing standard model theory? Really long name, lacustrine something.
Aeolian lacustrine.
Yeah.
Oh well, this was
the complex theory.
The complex theory for short. Well, in the 50s, Douglas Johnson, who was sort of the dean of geomorphological studies at where was he? One of the Ivy League colleges. He was at Columbia University. So there was this controversy from the 30s when the Carolina Bays first showed up as a object of interest, was after the first aerial surveys were being done in the early 30s, because up to that point nobody had seen them except from the ground, and they're not obvious from the ground. Mm-hmm. But Edwin Corlett, I think was his name. He was the engineer up in the New York office of Fairchild Aerial Surveys, who did this first survey, and he took all the prints, and he was the first one to lay out the mosaic and see these incredible formations, these elliptical formations, all with these almost perfectly parallel long axes of the ellipse. And his first impression was that it was probably something produced from his first impression. His first thought was, well, is this evidence of some kind of a meteor storm? So he contacted a friend of his, Frank Melton, who was with a school in Oklahoma, and he brought in his colleague Shriver, and they went up there and they looked at this. They looked at the mosaic that Corlett had laid out, and they said, yeah, that's what it looks like. It looks like, a meteor storm of some kind. So they did actually the first field work, and they published on it. And basically, I think the subtitle of their paper was, "Are They Meteorite Scars?" Well, this launched a controversy that lasted for about the next 20 to 25 years between a group that formed around studies at the Carolina Bays that believed they had an extraterrestrial origin, and another group that believed they were purely terrestrial, who had invoked various processes such as like karst type processes or sinkhole processes, right? And so this controversy raged between these two groups, the celestials on one side and the terrestrials on the other, without resolving it. And then in the 1950s, this Douglas Johnson wrote this big tome called The Origin of the Carolina Bays. He was the one who concocted the so-called complex theory, which was the Artesian solution lacustrine Aeolian theory.
Yeah.
Did you get that?
I think so.
Artesian solution lacustrine Aeolian theory. So in a sense, what he did was he got every geomorphic process you could basically think of and cobbled it all together to try to come up with some theory to explain every facet of these bizarre formations.
Okay, the kitchen sink theory.
Yeah.
The think and think theory. Yeah, the kitchen sink theory. Oh.
Okay, so it must have been, I think it must be potassium argon. Because the longest lived radioactive isotopes of argon, it has a half-life of only 269 years. But they say that KAR dating, or potassium argon dating, can date, is a geological dating process that they can use to date anything from 20,000 to 4 million years. So that sounds right.
Yeah, that sounds about right. Yeah. So that could have been what it is. I mean, there is an argon, but yeah, it might have been that. Like I said, I'm dredging stuff up from, literally 25 years ago. So.
Let me look up argon. I'll try that.
Well, I wanted to ask about typically the scientific process is, if you develop a theory, there's something in there that, essentially can be tested to falsify the theory, right?
Yes, you have to be. That's the idea. There has to be a way to test it to disprove it.
Exactly. So is that? Is there something like that in this the complex theory? Was there something that he left there that says if this is found or if this is not found, then my theory is not right?
Yes, absolutely. There was a way to falsify it, and what happened was, and I guess we're kind of getting ahead of ourselves a little bit because we'll reiterate this because we'll do a whole program just on the mystery of the Carolina Bays. But I'll say this. Yes, his theory was falsifiable. And what happened was, in a nutshell, this is what it required. There's limestone bedrock in the southeastern coastal plain. It tilts towards the ocean. It tilts to the southeast. In geological lingo, it dips towards the southeast, right? Now, in an artesian well, basically you have water running under two you'd call it it's a perched aquifer. It goes between two layers of bedrock where it's trapped. So you've got water coming from upstream. So because of that, and it's flowing down, and if it meets an obstruction, it's then going to be under pressure. Mm-hmm. So the idea is if that water under pressure finds an access point, some kind of an aperture, some kind of a fissure or crack in the overlying cap rock, in this case it would be limestone, what it does is it forces it up, right? It forces it up like this, and it rises under pressure to the surface, right? So that's an artesian well, right? Okay, so now you got this water coming up to the surface like this, but what you have to picture, it's almost like an upside down waterfall. And so as it's coming like this, it's eroding the limestone and migrating up current, right? Mm-hmm. So as it migrates up current, the idea is it's now dissolving the overlying sediment as it's moving, right? And creating almost like a sinkhole. So the four terms were artesian, solution, because it's dissolving the limestone. See, there's the solution part. It's dissolving the limestone to create this elongated fissure, if you will, right? So you've got artesian, solution, lacustrine means lake, right? It's just a long term for lake. So now this water rises to the surface, the land sinks, essentially forming a sinkhole. Now that water rising forms a lake. The final term is aeolian, which means wind. So now the wind blowing causes the currents to rotate in the lake, smoothing the shorelines of the lake into these almost perfect ellipses. And I'm going to do a screen share here because I did pull up the first mosaic that Corlett put together in the offices of, and I think it was 1932, 33, right in there, in the New York offices of Fairchild Aerial Surveys. And I'll do it.
Called it Spring Eroded Lake in the Wind. And that would have been way easier to remember.
What's that?
That's non-scientific, though, buddy.
Wait a second.
Argon dating has been invented to supersede potassium argon dating in accuracy. So you're correct.
Argon. Yeah, okay.
There you go.
And maybe about that time, maybe was in the transition period where they were shifting over to argon, because this was what, 27, 28 years ago. Okay, let's see here. Now, if I can get my share screen here. Share.
So, yeah, this is somewhere over South Carolina, right? His original photo mosaics from the aerial surveys.
Yeah.
So it has a half-life of approximately 1.25 billion years.
Ooh, okay.
Yeah.
Go. Well, this is what he was looking at.
There you go. Look at that.
Yeah. Now, what Davies is doing is amazing because he's doing this with LiDAR, and what it's showing. In fact, we should probably get him on here for a conversation, and he could bring on some of these beautiful examples of the LiDAR research that he's been doing, because one of the things he's discovered is that there are Carolina bays that you don't even see from above. They're buried, completely buried, but LiDAR, they show up. Yeah, he's done some really interesting stuff. But this goes back to the early 30s. This is the mosaic right here, and you can see these elliptical formations. No, but obviously there are rivers, and there are interesting features, that have to be explained by any theory. But so, to make a long story short, if you think about scenario that I just described, the complex theory, that means that the bottom of a bay should show some indication of this aperture that would have been eroded in the limestone.
Yeah.
And this aperture, this crack, if you want to call it that, just for a simple term, should generally align with the long axis of the bay, because that's the idea, is that the water is moving up under pressure and it's eroding its way uphill, basically. Up dip, you would say. And then at the end of that, so there now should essentially be almost like a karst-like formation, or should be a space, a gap between the limestone bedrock. Okay, so...
And every bay should have one of those.
And every bay should then have one of those. Exactly. So this was Douglas Johnson's complex theory. Okay, here's what happened. In the 1960s, for the first time, they started taking subsurface surveys of the bays, taking core samples of the bays. Well, after about a dozen of those efforts of tracking, mapping the bottom of the bays, taking core samples, doing gravimetric surveys, guess what? None of them had that slot that should have been there. Not one of them. So basically, that complex theory got quietly shelved. And for another 10 years or so, the weight of the argument kind of went back to the celestials until, I think it was about 77. Another paper came out, another treatment of the Carolina Bays called The Origin of the Carolina Bays. And basically this was an attempt to salvage what was left of Douglas Johnson's theory and come up with a variation on it to try to make it work. And what I remember is that, and I've actually got a copy of both of those. I've got Douglas Johnson's work, which I read through a couple of times. It is actually a very interesting read. It is. It's a very interesting read, in spite of the fact that at the end of it, he basically goes off and concocts a theory that makes no sense. But his observations were nonetheless interesting, and he certainly was of the mind that, yeah, this is a mystery that we need to try to explain. So this second treatment, what was his name? Somebody Koksarowski, I think was his last name. He and I'm not going to get into that now, but we certainly can get into that at when we devote, because we can easily devote an hour and a half or so to this discussion of the bays. And it's worth doing. It is worth doing, but certainly not with the impression that we're going to get any final solution to the mystery, but to lay out, and who knows, maybe somebody listening out there will have an original idea or be motivated to get out and try to solve the mystery. But we've got some interesting people who are working on it. And what we see is that the four scientifically oriented or scientists that I know that have worked on it have all come up with very different solutions to the problem. But anyways, we can go through some of Koksarowski's work, and I think I'll show you where the fatal flaws are in that, and then go back to some of the stuff that's occurred in the interim, and where it stands now. And
so we were just kind of sorry, Rand. I was just saying we were kind of reviewing what we went through last week, last episode with George Howard. You know, he's from or lives in Raleigh.
Yeah.
So a lot of these features are just to the southeast of Raleigh, going down the Cape Fear River, really from Fayetteville, which is south of Raleigh, toward the coastline in Wilmington. So, you know, he's very familiar because he's right in the bulk of them there.
Yeah.
Yep.
Can you see this? I'll leave it at this one. This will be the last image, because this beautifully shows the parallelism and how elegantly elliptical they are.
Right.
Yep. And there's another feature, and this is what we'll explore. They all have the most prominent rims to the southeast.
Yes, that's right.
And so when I was looking at the bays, you know, as you can see, I think maybe there we go. Oh, yeah. Okay, I've added axes to those. Now, the theory of the celestials was that this represented atmospheric flight paths of bolides entering the atmosphere. Because before the efforts to basically bring the whole argument back to the Earth and explain it in uniformitarian terms, the idea that had evolved post Melton and Shriver actually involved more of a, what we say, a storm of Tunguska-like events. And several of those, and this is what we'll get into in more detail, involved actually aerial bursts rather than impacts. So it may have been a combination of impacts. It may have been a combination of aerial bursts. But in any case, whether it turns out that it's celestial in origin, my thinking was, this is, again, going back to the late 80s and early 90s, is that, well, if these long axes represent flight paths, what happens if you project those to try to see the entry path of this presumably swarm of disintegrated, perhaps comet nuclei material coming into the atmosphere? And the first thing I realized was, well, it would have carried it right over the Laurentide ice sheet.
Yes.
So my next thing of thinking was I drew a path following this alignment right here, which is just about 45 degrees to the northwest. It led over not only the Laurentide ice sheet, but over the Cordilleran ice sheet as well. So then I thought, well, let's have a look and see what we see in terms of anything unusual or extreme occurring to the ice sheet about this time. And I might mention also that the Carolina Bays, at this point, by the 50s, radiocarbon dating had come online. And so you were having core samples taken of the bays. Now, when they did the subsurface surveys, what they discovered was that the bottom of the bays is this kind of unusual, almost like hard-packed. It was described by some of the researchers as baked clay, right? Mm-hmm. And of course, it was this baked clay that formed almost the bottom of these elliptical bowls, right? But in most cases, over that, and they called it, the term was humate that they used to describe this kind of unusual, dense, almost baked clay that formed the bottom of the base. But over there was a lot of peat and sedimentary accumulation that they had to core through. But what that meant was that by extracting cores, you could find, abundant organic material in those cores, and that material could be dated. And over and over and over again, the oldest dates that were coming up were terminal ice age. Nobody's mentioning it back then, but if you go back and look at it, you're seeing that it's coming up younger Dryas age. The dates were coming up 11, 12,000 years, 13,000 years, right in there over and over again. So that led the researchers to think that, well, they were all pretty much produced at the same time. These weren't things that were, forming, over long periods of time where, one might be forming and then it's halfway formed and then a new one starts forming. What it appeared was that they all formed simultaneously. And so that's part of the mystery, which to me, again, leads back to, I still don't see a plausible theory that relies exclusively on terrestrial processes, right? It still seems to me, and we'll get into this, we're definitely going to get into this. We're going to look in detail. For example, we will look in detail at impacts and what they do under various circumstances. We will look in detail at the event surrounding the Tunguska event of 1908. Once we are armed with that information, whatever insight we get to that, we'll come back to the bays, and then we will look at that. We will look at the updated controversies, then we'll leave it to the listener to see what they think. I, at this point, lean towards a celestial explanation only because I haven't seen anything that's exclusively terrestrial or gradualistic that can explain these things. So where does that leave us? Maybe we can, get some of the, maybe I'm sure Tony Zamora would be happy to come on and talk to us about his ice boulder hypothesis.
Yeah, that's one of my favorites.
Yeah. So, we could certainly do that.
Well,
I think.
Let's visit that briefly, though, because he attributes that to an impact in the Saginaw Bay of, the Mitten of Michigan. Is there any evidence out there that says that's a recent impact site?
Oblique. He thinks
not that I know of, other than topologically. It's a basin. The problem is that the theory that we're looking at now is that there were impacts into the ice sheet itself. And this is where I went, not knowing a whole lot about this, 25 and 30 years ago. Once I discovered this or came upon the idea that the entry path for the Carolina Bay, if it was a celestial, if it was a fragmentation type event, if Earth encountered a swarm of stuff, and we can look at the multiple evidence that suggests the flight path was from the northwest. If it comes over the ice sheet, and this is where Tony's idea is coming from, is that the impact into the ice sheet, the breccia that's thrown up in this case is going to be big chunks of ice instead of rock that's raining back down. And I know that idea has been challenged by Malcolm LeCompte. I don't know exactly what Malcolm LeCompte's specific objections are, but I know he disagrees with that. But I don't know. I would still lean towards, and once you see this, when we start looking in more detail at Tunguska, there actually is elliptical swamps in the region of Tunguska that were probably not there before the thing happened. So that's why I'm leaning towards a massive swarm of stuff coming in. But that doesn't mean that there couldn't have been that swarm might have been more like a satellites. It might have been the entourage that was accompanying much larger pieces. Yeah. And if these pieces splayed out over the ice sheet and hit the ice sheet, I think the explanation that we need to be looking at now is evidence that there were multiple impacts into the ice sheet. And that's what we're going to explore through this series, especially when we start looking at drumlins and some of the paths of the catastrophic meltwater paths. It'll take us right to that. And of course, when we go on field trips like the one next summer, we're going to be looking at some of the most spectacular erosional features on the planet. Yeah.
Wait for that.
I know. Me either. I can't wait, man. I was looking at this, looking on the maps, looking at some of the old photos from past expeditions just over the weekend and going, yeah, I'm ready. I'm ready to get back out there.
Let's go.
Yep. So, anyways, yeah, a lot of stuff to talk about. I mean, there's no shortage of content for us to explore in upcoming episodes.
Do you have stuff to add to about what George said about Hiawatha, or are we going
to? He seemed to cover it. I mean, I know there's evidence of a second crater.
Yes. Yeah, and he mentioned that. Yeah, but yes.
Yeah. So, if Brad, you'll notice Brad is sitting in front of a graphic that I did years ago, showing everywhere where it appears that there was catastrophic meltwater discharges from the late Wisconsin or late Pleistocene ice complex.
Ah, okay. I see.
That's what those blue arrows are. Yeah, I mean, for example, going over here, this is the Fennoscandian ice sheet over northwestern Europe, and there is evidence of catastrophic meltwater floods. Yep, coming off of those. We see gigantic flood features in the area of the Altai Mountains. We see drumlin fields in Ireland. We see tunnel valleys in Germany. We see scablands on the bottom of the North Sea. And then over here in North America, we have, in fact, I think Brad and I have looked at all of these except the one up here in the Northeast and this one, which is the Mackenzie River catastrophic flooding.
You can see where you're pointing, but
you can or can't?
Cannot. Brad has to point for us to see what's going on there.
Oh, Brad. Okay, Brad's attempting to point. Okay.
Yes, that's Mackenzie River up there headed north, right?
Yeah, yep. That's it up there.
What's a tunnel valley?
What's a what?
Did you say tunnel valley? Is that what you said?
Tunnel valley. That's what I said.
Yeah. What is that?
Well, it's a branching network of large stream cut valleys that were formed catastrophically through large scale floods.
All right.
We'll be looking at examples of those.
So yeah, you've got your flood arrows, and then recently, I guess, someone put the Hiawatha Crater impact site in the middle, and it's
Brad did that, I believe, didn't you, Brad?
Well, I added that because it was newsworthy at the time, and this is actually the very first video that I've got available on the Cosmographia 101 series. So I put that on there, though you don't talk about it at all because the video's from 12 years ago. So I got accused of doing clickbait, but it was just a topical thing, and I thought it was curious that it seems to be pretty much right in the center of that ice mass.
How dare you, Brad?
Yeah. I don't know what that means, but I just thought it was curious, so I went ahead and put it there on the thumbnail, and that's still one of the most popular videos because people do hear about Hiawatha Crater.
What do you mean clickbait? I mean,
it baits you into clicking the link.
Yeah, I know what clickbait is, but I don't understand how it applies to this.
Because you're not actually talking about Hiawatha Crater.
There's nothing in the video where we talk about Hiawatha Crater.
Right.
I see.
Because the icon they see has Hiawatha, they click and they watch for 2 hours and zero Hiawatha. That's called.
Okay, it's all becoming clear to me now. Okay. Well, what can I say?
Good job, Brad.
Where else was I supposed to put it? That seemed like the obvious place.
Well, I think it's a great illustration that impact is right in the center of all those outflows.
Mm-hmm. Yeah.
It's odd.
Yeah.
Interesting.
Well, the key, I think, is mapping the drainage features, mapping the patterns of meltwater drainage is what I'm talking about. And that's kind of what we've been doing. That's what I've been doing. And at some point we'll do a big reveal, and I'll show what that has led to. Because you see, here's the thing: when we look at the ice sheets of the Little Ice Age, which basically began melting back early to mid 19th century, what we see is that they basically are diminishing in size by marginal recession. Does that make sense? In other words, you've got a glacier that for 300 or 400 years has been growing down valley. This is very prominent in the Alps, for example. During the medieval warm period, glaciers were hugely contracted to what they were during the Little Ice Age. And they grew enormously during the Little Ice Age. I mean, there are examples of whole villages being overrun by the growing glaciers. It was really like this glacial nightmare to a lot of these people who were seeing their farms and their lands and their crops get completely swallowed up by these massive glaciers of the Little Ice Age. Now, of course, the Little Ice Age glaciers were diminutive compared to the Great Ice Age. But what happened was, because you had the Little Ice Age and it began ameliorating, not in the same place everywhere, but at different times, but it began ameliorating through the late 17 and into the 1800s, right? As the Little Ice Age, these enormously swollen glaciers of the Little Ice Age began to retract back, you had this group of scientists, or not, I would call it, at that time they were referred to as naturalists, or, naturalist philosophers or natural philosophers, right? Who were observing, okay, look, here's this big boulder here that was obviously, and look, we look at the granite bedrock here, but this is limestone. So where did the limestone was 20 miles away. So how did this boulder get here? Well, it was clearly quarried and transported by the glacier, right? As the glacier began to retract back, you look back and there's the layers of glacial till, right? And you could see for example, that glaciers are these dynamic things. They're not, it's almost, you have to almost picture like a multi-layered conveyor belt of ice that's moving. It's like living ice. It's moving and it's carrying material. And so when you get to the snout of the glacier, these conveyor belts are dumping this material and it forms a mound, right? And that is your terminal mooring. It's composed of glacial till. And glacial till is simply the ground mass that has been pulverized and ground up by the passage of this heavy glacier pushing over the land, right? So now when the glacier retracts, you can see it retracts back, and here it leaves this elongate, kind of arcuate mound that conforms to the snout of the glacier. Now, let's say the glacier recedes back and it pauses for a while. Well, in that pause, it will build another secondary terminal mooring. And in fact, there are places where you can see a succession of terminal moorings that show that the glacier retracted, paused, retracted, and paused. Okay, well, so during the Little Ice Age, while these glaciers are retracting, what happened is these guys going out there looking at that were able to see, okay, look, down here at the foothills of the Alps, we see these features. We see that, for example, the glacier retracts back and a chunk of ice gets left, right? Because it's retracting back, it's melting. There may be a piece of ice that breaks away and it's laying there in the glacial till, right? It continues to retract back, the ice melts, and it forms a puddle in this glacial till, because it might actually be embedded in the glacial till, right? Then it melts and it forms a lake. That's called a kettle lake, right? So they're looking at erratic boulders, they're looking at kettle lakes, they're seeing where meltwater flowed under the glaciers and then discharged right at the snout of the glacier. And where those meltwater tunnels were formed, once the glacier melted back, you could actually see a trace on the land because there's sediment being carried through those tunnels, right, that are at the bottom of the glacier. They're carrying sediment. So when the meltwater source, which is up glacier, finally terminates, the sediment gets left, and so when the glacier itself is gone, it's left these large, sinuous, elongated tracts on the landscape. Those are called eskers, right? So basically what happened was, as the Little Ice Age glaciers begin to retract, they're out there looking at this stuff. They're looking at the glacial till, they're looking at the mooring, they're looking at the erratic boulders, they're looking at the kettle lakes, they're looking at the all of this evidence, the eskers and so on. And as a result of that, they were able to then look and see that there was that same phenomena reproduced, but in a much larger scale. You see, because now they could look out onto the Jura Mountains, and there in the Jura Mountains, they're finding lithologies that are native to the Alps. And they're going, well, geez, that meant that while the Little Ice Age glaciers came down to the foot of the Alps, apparently you had glaciers that came all the way down and crossed a 30 or 40 or 50 mile valley and swallowed up the Jura Mountains. See, it was seeing the effects of the Little Ice Age that gave them the eyes to see the effects of the Big Ice Age. That's my whole point here.
That's awesome.
Right.
That's great.
Now, I have a second point to make. Here's the second point. The second point is that ordinarily, as the climate warmed out of the cold of the Little Ice Age between 1800 and 1850, and the ice began to recede, what we see is that it's a marginal recession. Basically, the snout of the glaciers melt. It's melting back faster than it's being fed from the source. In a glacier, in a living glacier, you've got the zone of accumulation at the top and the zone of ablation at the bottom. And in between, you've got this ice, this living ice, moving, flowing like a slow-moving flow, carrying this material down that it collects from the sides of the valleys, from the floor of the valleys. And then if you have two glaciers coming from two different valleys and they meet, right? Now you have what's called in between. You now get this thing, it's called a medial moraine. or along the sides of the glaciers, you'll have lateral mooring. But the point is that watching these glaciers shrink to a fraction of their swollen maximum during the Little Ice Age, 150 to 200 years ago, what we saw was basically they receded back from their margins. They melted from their margins, right? Now, when we look at the melting of the late Pleistocene, or I'll say late Wisconsin complex for North America, we do see, of course, marginal recession, but there's something else. We see epicenters of melting, catastrophic melting, that might be 500 miles or more from the margin of the ice sheet. You see what I'm getting at here? Yeah. So that's the problem. We cannot explain it because the geomorphic evidence is not consistent with a simple, prolonged marginal recession. There are melting epicenters, and so far, I don't see anybody explaining that.
This is Cosmographia, the Randall Carlson Podcast.